Welcome. Today we're diving into the fascinating world of neural networks, the core technology behind large language models, or LLMs. Neural networks are inspired by the structure of the human brain, aiming to replicate the way our neurons connect and communicate. This design allows machines to process information in a way that's surprisingly similar to how we think and learn. In this video, we'll explore how these networks work, why they're so powerful, and how they enable LLMs to understand and generate complex language. Let's start by understanding what a neural network actually is and why it's so important in artificial intelligence. Neural network is a computational model designed to mimic the way the human brain works. Just as our brains are made up of billions of neurons connected by synapses, a neural network consists of interconnected nodes, often called artificial neurons. These nodes are organized in layers, and each connection between them carries a weight, which determines how strongly information is passed along. By adjusting these weights, neural networks can learn to recognize patterns, make predictions, and solve complex problems. This ability to learn from data is what makes neural networks so powerful in the world of artificial intelligence. Neural networks are specifically designed to imitate the way our brains process information. In the human brain, neurons receive signals, process them, and pass them on to other neurons. Similarly, in a neural network, artificial neurons receive input, perform calculations, and send the results to the next layer. This layered approach allows the network to build up complex understanding from simple pieces of information. Over time, as the network is exposed to more data, it becomes better at recognizing patterns and making decisions, much like how we learn from experience. Neural networks are made up of multiple layers, each with its own specific role. The first layer, called the input layer, receives raw data. Next, hidden layers process this information, extracting features and patterns. Finally, the output layer produces the result, such as a prediction or classification. The use of multiple layers allows the network to learn increasingly complex relationships within the data. This structure is what gives neural networks their remarkable ability to handle tasks like language understanding, image recognition, and much more. The core of every neural network are mathematical functions. Each artificial neuron takes in inputs, applies a mathematical function often called an activation function, and produces an output. These functions help the network decide which information is important and which can be ignored. By combining many such functions across layers, neural networks can model highly complex relationships in data. This mathematical foundation is what enables neural networks to learn and adapt over time, making them incredibly versatile tools in artificial intelligence. One of the most impressive features of neural networks is their ability to learn complex patterns from data. As the network is trained, it adjusts the weights of its connections to better predict outcomes or recognize features. This process, known as training, allows the network to improve its performance over time. Whether it's identifying objects in images or understanding the nuances of human language, neural networks excel at finding patterns that would be difficult for humans to spot manually. Data is the fuel that powers neural networks. During training, the network is exposed to vast amounts of data, which it uses to learn and refine its understanding. The more diverse and comprehensive the data, the better the network becomes at generalizing and making accurate predictions. This reliance on data is why large language models require enormous datasets to achieve high performance. Without enough data, even the most sophisticated neural network would struggle to learn effectively. In a neural network, every connection between artificial neurons has a weight, which determines how much influence one neuron has on another. During training, these weights are adjusted based on the network's performance. If the network makes a mistake, the weights are tweaked to reduce future errors. Over time, this process helps the network become more accurate and reliable. Understanding how weights work is key to grasping how neural networks learn and adapt. Activation functions are a crucial part of neural networks. They determine whether a neuron should be activated or not, based on the input it receives. Common activation functions include sigmoid, tan, and ReLU. Each function has its own strengths and is chosen based on the specific task the network is trying to accomplish. By using different activation functions, neural networks can model a wide range of behaviors and solve various types of problems. Word propagation is the process by which data moves through a neural network. Starting at the input layer, information is passed from one layer to the next, with each neuron applying its mathematical function. The final output is produced at the last layer, representing the network's prediction or classification. This step is essential for making predictions and is repeated every time the network processes new data. Backpropagation is the learning algorithm used by neural networks to improve their performance. After making a prediction, the network compares its output to the correct answer and calculates the error. This error is then propagated backward through the network, and the weights are adjusted to minimize future mistakes. Backpropagation is what enables neural networks to learn from their errors and become more accurate over time. Training a neural network involves feeding it large amounts of data and allowing it to adjust its weights through backpropagation. This process is repeated many times, with the network gradually improving its ability to make accurate predictions. Training can take hours, days, or even weeks, depending on the complexity of the network and the size of the dataset. The end result is a model that can perform tasks like language translation, image recognition, and more. One challenge in training neural networks is overfitting, where the model learns the training data too well and fails to generalize to new data. To prevent this, techniques like regularization and dropout are used. These methods help the network focus on the most important patterns, rather than memorizing every detail. The goal is to create a model that performs well on both the training data and unseen examples. Regularization is a set of techniques used to prevent overfitting in neural networks. By adding penalties for overly complex models, regularization encourages the network to find simpler, more general solutions. Common methods include L1 and L2 regularization, which add constraints to the weights. These techniques help ensure that the model remains flexible and performs well on new data. Dropout is another technique used to improve the robustness of neural networks. During training, dropout randomly disables a fraction of the neurons in the network, forcing the remaining neurons to work harder and learn more robust features. This helps prevent the network from becoming too reliant on any single neuron and improves its ability to generalize to new data. Large language models, or LLMs, are built on top of neural networks. These models use deep neural networks with many layers to process and generate human-like language. By training on massive datasets, LLMs learn to understand context, grammar, and meaning, enabling them to produce coherent and relevant text. Neural networks are the foundation that makes this possible. Deep learning refers to neural networks with many layers, known as deep neural networks. These networks can learn highly complex patterns by processing data through multiple stages. Deep learning is what enables LLMs to handle tasks like translation, summarization, and question answering with remarkable accuracy. The depth of these networks is what sets them apart from simpler models. LLMs are trained on vast amounts of text data, including books, articles, and websites. This diverse input allows the model to learn the intricacies of language, from grammar and vocabulary to context and meaning. The quality and quantity of input data play a crucial role in determining the performance of the final model. The more data the model sees, the better it becomes at understanding and generating language. For data can be processed by a neural network, it must be broken down into smaller pieces called tokens. Tokenization is the process of splitting text into words, subwords, or even characters. This step is essential for enabling the network to understand and process language efficiently. By working with tokens, neural networks can handle a wide variety of languages and writing styles. Once text is tokenized, each token is converted into a numerical representation called an embedding. Embeddings capture the meaning and context of words in a way that neural networks can understand. These representations allow the network to process language more effectively, recognizing similarities and relationships between words. Embeddings are a key component in making neural networks work for language tasks. Attention mechanisms are a powerful addition to neural networks, especially in language models. They allow the network to focus on the most relevant parts of the input when making predictions. By assigning different weights to different tokens, attention mechanisms help the model understand context and relationships within the text. This leads to more accurate and coherent language generation. Transformers are a type of neural network architecture that has revolutionized language modeling. They use attention mechanisms to process input data in parallel, making them faster and more efficient than previous models. Transformers are the backbone of modern LLMs, enabling them to handle long sequences of text and generate high-quality language output. One of the key advantages of transformers is their ability to process data in parallel. Unlike older models that handled data sequentially, transformers can analyze multiple parts of the input at once. This parallel processing makes training and inference much faster, allowing LLMs to handle massive datasets and generate responses in real time. Self-attention is a mechanism that allows each token in the input to consider every other token when making predictions. This helps the model capture relationships and dependencies within the text, leading to more accurate understanding and generation. Self-attention is a core component of transformer architectures and is essential for the success of modern LLMs. Since transformers process all tokens in parallel, they need a way to keep track of the order of words. Positional encoding is a technique that adds information about the position of each token in the sequence. This allows the model to understand the structure of sentences and maintain the correct order when generating language. In addition to attention mechanisms, transformers use feed-forward layers to process information. These layers apply mathematical functions to the data, helping the model learn complex relationships. By combining attention and feed-forward layers, transformers achieve a balance between understanding context and extracting features from the input. Transformers and other deep neural networks achieve their power by stacking many layers on top of each other. Each layer processes the data in a slightly different way, allowing the model to learn increasingly complex patterns. The depth of the network is what enables it to handle challenging tasks like language understanding and generation. Once the neural network has processed the input data, it generates an output. In the case of LLMs, this output is typically a sequence of words or sentences. The model uses its learned knowledge to produce language that is coherent, relevant, and contextually appropriate. Output generation is the final step in the neural network's workflow. After training, neural networks are evaluated to determine how well they perform on new data. Metrics like accuracy, precision, and recall are used to measure performance. Evaluation helps identify areas where the model excels and where it may need improvement. This step is essential for ensuring that the neural network meets the desired standards. Fine-tuning is the process of adjusting a pre-trained neural network to perform better on a specific task. By training the model on a smaller, task-specific dataset, it can learn the nuances of the new task while retaining its general knowledge. Fine-tuning is commonly used to adapt LLMs for specialized applications, such as medical or legal language processing. Transfer learning is a technique where a neural network trained on one task is adapted for another related task. This approach leverages the knowledge the model has already gained, reducing the amount of data and time needed for training. Transfer learning is a key reason why LLMs can be quickly adapted to new domains and languages. Neural networks are highly scalable, meaning they can be expanded to handle larger datasets and more complex tasks. By adding more layers or increasing the number of neurons, networks can tackle increasingly challenging problems. Scalability is one of the reasons why neural networks are used in everything from image recognition to natural language processing. Training and running neural networks require powerful hardware, such as GPUs and TPUs. These specialized processors are designed to handle the massive computations involved in neural network operations. Advances in hardware have made it possible to train larger and more complex models, pushing the boundaries of what neural networks can achieve. Neural networks are used in a wide range of applications, from language translation and image recognition to medical diagnosis and financial forecasting. Their ability to learn complex patterns makes them invaluable tools in many fields. As technology advances, the range of applications for neural networks continues to grow. Despite their power, neural networks face several challenges. These include the need for large amounts of data, the risk of overfitting, and the difficulty of interpreting how the network makes decisions. Researchers are constantly working to address these challenges and make neural networks more reliable and transparent. Understanding how neural networks make decisions is a major area of research. Techniques like visualization and feature importance analysis help shed light on the inner workings of these models. Improved interpretability can lead to more trustworthy and effective neural networks, especially in critical applications like healthcare. As neural networks become more powerful, ethical considerations are increasingly important. Issues like bias, fairness, and transparency must be addressed to ensure that these models are used responsibly. Ongoing research and regulation aim to create guidelines for the ethical use of neural networks in society. Future of neural networks is bright with ongoing advancements in algorithms, hardware, and applications. Researchers are exploring new architectures and training methods to make networks even more powerful and efficient. As these technologies evolve, we can expect neural networks to play an even greater role in shaping our world. Neural networks are not just tools for analysis, they're also being used to generate creative content. From composing music and writing poetry to creating artwork, neural networks are pushing the boundaries of what machines can do. This creative potential opens up exciting new possibilities for art, entertainment, and beyond. You might not realize it, but neural networks are already a part of your daily life. They power voice assistants, recommend movies and music, and even help filter spam emails. As these models become more advanced, their impact on our everyday experiences will only continue to grow. Neural networks are most effective when they work alongside humans. By combining human intuition with machine learning, we can solve problems that neither could tackle alone. This collaboration is leading to breakthroughs in fields like medicine, engineering, and creative arts. Neural networks can continue learning even after they've been deployed. Through techniques like online learning and reinforcement learning, models can adapt to new data and changing environments. This ability to learn continuously makes neural networks highly adaptable and resilient. Despite their strengths, neural networks have limitations. They require large amounts of data and computational power, and they can sometimes make mistakes that are hard to explain. Understanding these limitations is important for using neural networks effectively and responsibly. Researchers are constantly working to improve neural networks. This includes developing new architectures, optimizing training methods, and finding ways to make models more efficient and interpretable. These efforts are driving the rapid progress we see in artificial intelligence today. Sum up, neural networks are the backbone of large language models and many other AI technologies. By mimicking the human brain, processing data through mathematical functions, and learning complex patterns, they enable machines to perform tasks that were once thought impossible. As research continues, we can expect neural networks to become even more powerful, versatile, and integrated into our daily lives.